Hi everyone, I'm really excited to tell you about a paper where we use social choice to find common ground or compromise alternatives in settings such as those where these alternatives are pieces of text, so there are many alternatives to choose from. And this is joint work with wonderful collaborators, Jay, Ariel, Ben, and Shirley, all of them at Harvard. Our point of departure are experiments to integrate deliberation with AI. Deliberation has in part been so interesting because our societies are so polarized these days. So people don't spend a lot of time talking politics to people they disagree with. And AI might be a way to scale up deliberation to more people. One of these proposals is due to M.H. Tesler et al. In a paper that they published in Science 2 years ago, where they built what they call the Habermas machine. It's a pretty complicated setup, but I'll tell you about how it's built. In these deliberations, there's a topic, for example, what should guide policy on abortion? And then the participants in this case don't talk to each other, but they talk to a centralized AI system and provided with text that encapsulates a lot of their opinion about the topic. Tesla et al. Then fine-tuned a large language model that takes in the topic and the text written by the participants, and it has been fine-tuned to produce group statements, so statements that are supposed to encapsulate the things that people agree on, a statement that can find wide appeal among the participants. And these LLMs are non-deterministic, so they don't always generate the same piece of text if you ask them several times. And because of that, Tesla et al. Takes 16 samples from this LLM, which I'm naming here A through P. Tesla et al. Have trained another AI model to predict whether a participant would agree with a statement. And they use these proxies to rank these 16 statements from the perspective of each of the participants. We're now in a social choice setting. We have, very classically, 16 statements, we have complete rankings over them. And because of that, Tesla et al. Can use a voting rule, in this case the Schulze method, to determine the winner. But this is only the very first part. You might notice that it defines a probability distribution over winning statements. There was no interaction with the participants after the first round. So Tesla et al. Sample from this process 4 times. They get 4 statements. They show them to the actual participants who rank them. And they use the Schulze method again to produce a winner. And then there's even more stages, but I want to leave it at that for simplicity. What Tesla et al. Show, and which is quite exciting, is that if these participants just talk to the AI and then read this winning statement at the end of this process, they update their opinions in a common direction in a way that resembles the outcome of classical deliberation. And so maybe with this very fast process, we can get some of the benefits of deliberation much cheaper and at scale. But our question is whether the Schulze method really was the right tool for its building block in this process. And in my mind, there are 2 big concerns here. The first concern is, does the Schulze method really return alternatives that represent common ground or compromise? And we don't really see a good reason for it to do that. One reason is something that typically we actually really like. The Schulze method is Condorcet consistent, but that means that it is inherently somewhat majoritarian, rather than trying to also keep minorities happy. So we don't think that's a perfect fit. And then the second point is that in both of the levels where the Schulze method is used, the inputs are just samples from some probability distribution. And so really, we should be aiming to satisfy some axioms, not relative to these samples, but relative to the distribution. And I don't see a clear argument for how the winner of the Schulze method on these samples guarantees something very important relative to the distribution. That, of course, is an opportunity for research. So we want to ask, from the perspective of social choice theory, what would be principled axioms and principled voting rules for this kind of setting? We think that an idea by Hervé Moulin is a really good point of departure, namely the proportional veto core. Let me explain to you how it works. So Moulin is in a very classical setting, n voters, m alternatives. The voters rank all the alternatives. And he says that a coalition of voters, capital S, has a veto power that is m, the number of alternatives, times the fraction of the coalition among all the voters, S divided by n. And then Moulin says that S blocks an alternative A if this veto power is strictly more than the number of alternatives that anybody in S ranks weakly below A. So here's an example where we have a coalition S of 4 voters among a total electorate of 12. There are 13 alternatives overall, and these are the suffixes of their preferences. So in this case, the alternative A has 4 different alternatives that somebody weakly ranks below them in the coalition, namely A, B, C, and D. And so if we want to figure out if this coalition blocks A, then we multiply n with the size of the coalition 4 divided by n, which in this case is strictly more than 4, which is the number of these alternatives that somebody ranks weakly below A. So A is blocked, which means that A is not in the PVC, which consists of all the unblocked alternatives, and a voting rule that satisfies the PVC can never return A as a winner on this kind of instance. I don't have time to really go into this, but I'm so excited about the fact that this axiom gives some rights to minority groups in a single winner setting. And so it brings some of the things that we really like about the proportionality guarantees in multi-winner elections, where it's easy to guarantee to a small group one of the members of the committee. It brings that into a single winner setting. So we think that this is really exciting, and it will ensure that minorities do have some influence on the output, which is something that we want for common ground. We'll actually adapt the PVC in two different ways. The first way is that for us, the alternatives come from some probability distribution. They should be weighted according to their probability mass in this distribution. And second of all, we'll also have some additive relaxation by some epsilon that's non-negative. So from now on, we have n voters, we have a probability distribution curly D over the alternatives, and we continue to have these complete ordinal preferences. The alternatives might even be infinitely many, that does not matter. We now say the coalition S blocks A if the proportion of S among the electorate is strictly more than the sum of probability masses of the alternatives that anybody in S ranks weakly below A, or the probability measure. So this is just rescaling everything to now be between 0 and 1 rather than 0 and m. Then we also introduce this epsilon slack, so S epsilon blocks A if this inequality even holds if we tighten it by an additive epsilon. The epsilon PVC are all the epsilon unblocked alternatives, and you might notice that if curly D is the uniform distribution over alternatives, and we set epsilon to 0, then we just get back the classic PVC. One way in which this definition of the epsilon relaxed PVC pays off is that we can now define a measure for how close an alternative is to being in the proportional veto core. We say that an alternative A's critical epsilon is the smallest epsilon for which A is in the epsilon PVC, and a smaller epsilon means that it's closer to being in the PVC. Conceptually, there's a better candidate for finding common ground. So now to our model. We have, as before, n voters, we have this probability distribution over alternatives, and we have complete rankings. And there might be many alternatives and many voters. Because of that, the distribution and the rankings will not be part of the voting rule's input. Instead, the voting rule has to access them through queries. There are only two queries. One query is really simple. It's a sampling query. So the voting rule can sample an alternative from curly D. And the second is what we call a min query, where we select a voter and we select a finite set of alternatives capital X, and the voter tells us which of the alternatives in X they like least. And of course, this could be implemented with pairwise comparison queries. We have some results on that in the paper, but I'll leave them out for conciseness. And our goal is to have a voting rule that only uses few queries and that finds an alternative with small critical epsilon. Let me show you what the voting rule is. It's fairly simple. The voting rule starts by using a bunch of sampling queries and to put all their outputs into this multiset capital X. Then there's a loop that continues as long as X contains strictly more than one alternative, and we'll always be removing one. And in each iteration of the loop, we pick a uniformly chosen voter, I. We ask I with a min query what they like least among the set X, and we remove it or one copy of it from X, and then we recurse. And at some point, of course, X will only have one alternative left, and that's the winner of the voting rule. First of all, this voting rule has some resemblance to the vote by veto procedure by Moulin. I want to give credit to him. And what we can show is that the output of this voting rule will be in the epsilon PVC with a probability of at least 1 minus delta. And epsilon and delta, of course, are these parameters that will determine exactly how many samples we need in the first step. One of the important things to point out here is that the running time of this voting rule is completely independent of the number of voters n. So if we're selecting common ground for 5 people or for the entire United States, it's also independent of the number of alternatives. The alternatives could be the space of all pieces of text that the LLM can generate, tremendously large. It will not bother this voting rule. We have some lower bounds as well. I just showed you that with this number of sampling queries, which scales as 1 divided by epsilon squared, and then has this log term, log 1 divided by epsilon times delta, With that, we can be in the epsilon PVC with probability 1 minus delta. And we have two lower bounds that are essentially matching, and we have them for both kinds of queries. So first, we show that even if we had unlimited min queries, if they were free, that the number of sampling queries we would need is essentially exactly the number of sampling queries that we do indeed end up using, except that we don't have this epsilon in the log factor. So there's a little bit of a logarithmic gap between the lower bound and the upper bound, but it's almost tight. We have the same kind of theorem also just for the min queries, assuming that the sampling queries are free. Let me switch over to the empirical experiments of our paper. The big question that we have is the extent to which classical voting rules, or also even just generations by large language models, will get close to this ideal of being in the PVC. And we investigate this on a synthetic experiment. Everything will be based on large language models. Let me lay it out. We start with a data set of personas. They come from a Stanford group, Castricato et al., who designed these LLM personas that are calibrated to the US census. So they're a decent stand-in for the US adult population. We have these personas, 815 of them, and we have 6 policy topics. For each of the 6 policy topics, we 10 times subsample 100 voters from the personas and 100 statements, each based on one of the personas to ensure some diversity. We, with an LLM, simulate a ranking of all these 100 statements by each of the 100 voters to get this ranking matrix of size 100 by 100. The next step is that we want to investigate the generalization. Even though we will only see a subset of the alternatives and a subset of the voters, this should say something about the full distribution of alternatives. It should say something about the full electorate. And to simulate this, we 4 times take subsamples of just 20 voters and 20 alternatives. And on this sub-ranking, we can then run something like Schulze-Boda, a classical voting rule, or we can give this to a large language model to generate a good compromise statement. And we will evaluate the statements that are produced by these voting rules and LLMs in terms of their critical epsilon. But crucially, the critical epsilon is not just with respect to the 20 voters and 20 alternatives, but the full latent set of 100 voters and 100 alternatives. Let me start with the results for the classical voting rules. I will show you the critical epsilon averaged over 3 topics. I'll choose the more polarized ones because the trends there are most visible. And then each one, as I've explained to you, is averaged over 40 runs. The first voting rule, veto by consumption, has a critical epsilon of almost 0. Veto by consumption is actually guaranteed to be in the proportional veto core for the 20 voters and 20 alternatives, but there might still be a bit of generalization error. And so this is why this is not quite 0. And then we consistently see this trend where veto by consumption does better than Boda, which is better than Schulze, which is better than IRV, and which is better than plurality. And plurality, and sometimes also IRV, can be worse than just choosing one of the 100 alternatives uniformly at random. And so this shows you that they are not doing really well at determining something that is in the PVC. In case you're struck by the fact that the absolute magnitudes here are relatively small, I want to remind you that critical epsilon is on a scale between 0 and 1, and each percentage point in this case essentially represents some coalition's veto power being violated on average by 1 person's worth. So in addition to these classical voting rules, we also want to investigate large language model generation. I'll make some space in this figure, just keeping veto by consumption and the random benchmark. We can use large language model generation in one shot. We'll use GPT Mini for this generation. And one power that this has is that it actually gets to write a completely new statement. And so, for example, we know that LLMs can sometimes be very smooth talking writers. And so maybe that's a really strong power where you can actually write something that makes lots of people much happier than anything among the 20 statements that were given to the voting rules. A first baseline is blind, so it only sees the topic. It doesn't even see anything about the voters. And this gives us a critical epsilon that is worse than Schulze, but for example, better than IRV. And then we have 2 better comparisons, where GPT Mini is also shown the 20 alternative statements, and it either sees the rankings or it sees the personas of the 20 voters. In both cases, we get a critical epsilon that is similar to Schulze. This shows some strength of LLMs. They have good priors about what a good compromise statement is for the US population. But this is also a liability. And to show you this, as our final experiment, I will zoom in our experiments just on experiments for a subset of the personas that by keywords we identify as being conservative, and then we rerun these experiments just on this population. So far, the critical epsilons are exactly as before, just the y-scale is rescaled. And now we switch to just the conservatives, and we see that the critical epsilon by veto by consumption hasn't really budged. And this makes sense because veto by consumption and all these classical voting rules are actually based on the rankings by the voters in the data set. We see that the random baseline becomes much harder because just choosing a statement at random will not be a good fit on average for this conservative subpopulation. And GPT has a bit of a similar problem. If GPT is blind and only sees the topic, it will also choose something that's a good summary for the US population, but a bad summary for a conservative subpopulation. So its critical epsilon is quite high. And if we feed GPT more information about our voters, then its critical epsilon goes down. So it does move towards this conservative population, but it seems like there's some fight between the information it actually has about the voters it's supposed to represent and its priors about what a good consensus statement is. And so because of that, even the best version of it still has a critical epsilon around 4%, which is not that great. So let me wrap up with 2 take-home messages. One take-home message is that I think that the PVC is just a fantastic axiom, and it deserves more study in our community. It's just so wonderful to have an axiom for single winner social choice that is not just relational, that is not just something that holds for certain kinds of inputs, that actually gives some proportionality guarantees in a single winner setting. I think this is fantastic, and I'm really glad that it's seeing more attention, but I think much more remains to be done. And then finally, I think the last 2 slides make a very nice story about the relative strengths and weaknesses of AI and social choice. We see that these priors embedded in a large language model about what people actually like, what is actually a good compromise, are a real asset that would be hard to replicate just with classical social choice. But we also see that this can be a liability when these priors are not in tune with the actual people we're trying to represent and their preferences. And so I think this really points to the necessity to combine voting and AI, as for example the Habermas machine does, and I think our community will have much more to study in terms of different ways of combining these 2 elements. Thanks a lot, and I look forward to seeing you in Rome.